When you gaze at the night sky, it feels as though you are witnessing the entire story of the universe. The sparkling stars, the glowing path of the Milky Way, the faint clusters of distant galaxies. But in reality, all of this brilliance, every planet, every star, every galaxy we can observe, even with our most advanced instruments, accounts for less than 5% of what truly exists. The rest of the cosmos, 95% of it, is hidden in plain sight, invisible and untouchable. Yet its presence dictates everything. This vast unseen domain is divided into two mysterious entities, dark matter and dark energy. Their names are simple, but the mysteries they represent are staggering, for they are the invisible framework and the driving force of the universe. Dark matter is the unseen scaffolding that holds galaxies together, while dark energy is the cosmic accelerator stretching the very fabric of space. Together, they determine the fate of the universe itself. The story begins in the 1930s, when Swiss astrophysicist Fritz Zwicky observed the Coma Cluster, a sprawling collection of galaxies. He noticed that the galaxies were moving far too fast to be explained by the visible mass alone. According to Newton's laws, they should have flown apart into the void, and yet they did not. Zwicky proposed that some invisible substance was providing the necessary gravitational glue. He called it Dunkel Materie, dark matter. His idea was radical, dismissed by many at the time, yet it planted a seed that would grow decades later. In the 1970s, astronomer Vera Rubin, working with Kent Ford, studied the rotation of spiral galaxies. What she found was revolutionary. Instead of slowing down at the edges, as expected, stars maintained nearly constant speeds across galaxies. The only explanation was that galaxies were surrounded by vast halos of unseen mass. Rubin's work cemented the existence of dark matter as a fundamental component of the cosmos. But what is it made of? That remains one of the greatest unsolved mysteries. Some theories suggest WIMPs, weakly interacting massive particles, that rarely interact with normal matter, slipping through stars, planets, and even our own bodies without leaving a trace. Others suggest axions, theoretical particles predicted by extensions of quantum field theory. Supersymmetry, a proposed expansion of the standard model of particle physics, offers exotic candidates. There is even speculation that dark matter could consist of primordial black holes, born in the earliest moments after the Big Bang. Despite immense efforts, experiments like ELU-X, Panda-X, Xenon 1T, and detectors buried deep underground or even in space have yet to find conclusive evidence. The silence of these experiments is itself an answer. It tells us that dark matter is even stranger than we dared to expect. Then, in 1998, came a revelation that shocked the scientific world. Two teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Zia Supernova Search Team, led by Brian Schmidt and Adam Rees, set out to measure the rate of cosmic expansion by studying distant type Ia supernovae. These stellar explosions, known for their consistency and brightness, served as cosmic lighthouses. The expectation was clear. The expansion of the universe should be slowing down under the pull of gravity. But the data revealed the unthinkable. The universe was not slowing, it was accelerating. Some unknown force was pushing space apart, driving galaxies away from one another faster and faster. This force was named dark energy, and it changed our view of the cosmos forever. Today, we estimate that dark energy makes up about 70% of the universe, while dark matter accounts for about 25%. Ordinary matter, everything familiar, everything we can touch, makes up only 5%. Think about that for a moment. Everything we have ever known, every book, every thought, every planet, every galaxy, all of human history and all of biology is just a thin sliver of reality. The true bulk of existence is hidden. Dark energy, unlike matter, does not clump or cluster. Instead, it acts as a uniform pressure woven into the fabric of space itself. It could be Einstein's cosmological constant, a term he once introduced and then rejected. Or it could be something dynamic, like quintessence, a field evolving with time. If dark energy remains constant, the universe may face the big freeze, an endless expansion leading to a cold, empty cosmos, where stars burn out, galaxies fade, and only black holes remain, slowly evaporating into nothing. If dark energy grows stronger, the expansion will accelerate to catastrophic extremes, tearing galaxies, stars, planets, even atoms apart in the Big Rip. If it reverses, the universe could collapse back on itself in a big crunch. Each possibility is written into the equations of physics, and we do not yet know which future awaits us. Some scientists, like Stephen Hawking, Michio Kaku, and Lisa Randall, have speculated that solving the mystery of dark matter and dark energy will require new physics. String theory suggests the existence of hidden dimensions, and perhaps these invisible forces are echoes from realms beyond our perception. The multiverse hypothesis even dares to suggest that our universe is one bubble in a cosmic foam, and dark energy might represent the interaction of our bubble with others. Imagine that what we perceive as cosmic acceleration is not a property of space itself, but the gravitational tug of neighboring universes just beyond our reach. The cosmic microwave background, the faint afterglow of the Big Bang, has been mapped in exquisite detail by satellites like WMAP and Planck. These maps reveal tiny fluctuations, ripples in the early universe that allowed galaxies to form. From this data, scientists derived the cosmic recipe: 5% ordinary matter, 25% dark matter, 70% dark energy. This is one of the most profound discoveries in science, and yet it leaves us humbled, for the recipe tells us the proportions, not the ingredients. We know how much, but not what. Some physicists argue that perhaps we are asking the wrong questions. Maybe dark matter is not made of particles at all. Maybe dark energy is not a mysterious pressure, but instead a sign that our understanding of gravity itself is flawed. Modified Newtonian dynamics, or MOND, suggests that Newton's laws break down at galactic scales. More radical theories propose that Einstein's general relativity must be expanded. Could it be that what we interpret as dark matter and dark energy are not entities, but symptoms of incomplete physics? This possibility remains controversial, but it demonstrates that science is willing to challenge even its most sacred ideas in search of truth. And what of the philosophical implications? Imagine living in a universe where 95% of reality is invisible. It challenges our very notion of knowledge, of existence. For millennia, humans believed the Earth was the center of the universe, only to discover that it is a small planet orbiting an average star in one of billions of galaxies. Now we face an even more humbling truth. All the stars, all the galaxies, everything we once thought was the universe is just the surface of a much deeper mystery. Plato's allegory of the cave becomes eerily real. What if what we see is only shadows on the wall, while the true essence lies forever hidden? Writers and thinkers throughout history have imagined such mysteries. Arthur C. Clarke once wrote, "Any sufficiently advanced technology is indistinguishable from magic." Perhaps dark matter and dark energy are today's magic, waiting for future generations to uncover. Isaac Asimov dreamed of universes within universes, while modern cosmologists wonder whether we are already surrounded by unseen layers of reality. Every discovery raises more questions than answers, and each question deepens the mystery. Even as we search, the practical possibilities spark the imagination. If dark matter interacts only through gravity, could advanced civilizations one day harness it, manipulating gravity itself? Could dark energy be tapped as a cosmic power source, an engine driving intergalactic travel? To us, these ideas seem like science fiction, but so did black holes, once considered absurd, until we captured their image with the Event Horizon Telescope. And so, as you listen to this, think of the stars above you. Think of the galaxies, each one a city of billions of suns, floating in invisible halos of dark matter. Think of the space between them, not as emptiness, but as a battlefield where dark energy stretches space itself. Imagine a future where the night sky grows darker, where galaxies slip beyond sight until only silence remains. Imagine another future where the universe collapses in fire or tears apart in chaos. These are not fantasies. They are real possibilities, written into the equations of our cosmos. We live at a unique moment in history. For the first time, humanity is aware of its ignorance. We know that we are blind to most of reality, and yet we also know that this blindness can be overcome. Every new discovery pushes back the veil, if only a little. Perhaps one day, long after us, future scientists will look back and smile at our confusion, just as we smile at the ancients who thought the stars were holes in a celestial dome. Until then, we live in mystery. And maybe that is the greatest gift of all. The knowledge that the universe is not small, not simple, but vast and filled with secrets we have only just begun to touch. So tonight, as you close your eyes, remember, what you see is only 5% of reality. The true universe lies hidden in darkness, shaping your world in ways you cannot yet imagine. And perhaps in dreams, you will drift closer to the truth.